Okay, can you introduce me or can start?
Yes, yes. I will start now. Uh, I I will start you now. Okay.
Okay, so
Okay. Good afternoon, everyone. We are starting the second SBE webinar, and today you have the participation of Professor Fabiana Arduini from Tor Vergata University. Professor Arduini has PhD in analytical chemistry from the Department of Chemical Science and Technology from Tor Vergata University. Currently, she is an associate professor in the same university. Since 2019, she is the CEO of the Sense4Med startup spin-off. Professor Arduini was coordinator of Interdivisional Sensor Group, Italian Chemical Society. Professor Fabiana is still associate editor of Microchemical Journal. Her research included the development of biosci and biosensor system, electrochemical biosensors, electrochemical mediator, screen-printed electrode, sensors and biosensors modified with nanomaterials, paper-based biosensor. Her extensive publication record includes over 2,000 papers and age index of 63 and more than 10,000 citations. Fabiana, feel free to start, and we will have a question from the audience. In the name of the SBE, thank you very much for you accepted for the webinar. Thank you.
So thanks for the introduction. Just to share my video. Okay, yeah, perfect. Okay. Are you able to see my screen?
Yes.
Okay, wonderful. So
Okay.
thanks for the introduction. Of course, for the invitation. It's a pleasure to be here, even if online. So just a few words about my university. My university is located at Rome, so in Italy, and is the second university in Rome. Here I reported the different department. I belong from Department of Chemical Science and Technologies, which is selected among the excellence department from Italian Ministry of the Research. And just a few words about my curriculum, already presented by the chairman, and I'm a full professor. I'm working not only in academic world as reported, but also my opinion is that sometimes it's very important that also the professor at university can boost the pass from the bench of the market. The reason for that, I was involved in several spin-offs, and now I'm a CEO of Sense4Med. I'm also part of another spin-off, the name is TechnoSense, which the electrochemical sensor now is on the market for water modeling control. And also part of, for example, the committee selected by Italian Ministry of Defense for the use my expertise to evaluate, for example, the risk for the soldier when go out in mission. So what I will present today is like a roadmap that we carried out in my group regarding the paper-based electrochemical sensor. So, because I'm part also by committee university by sustainability, and of course, if you think about sensor is conceived as sustainable device. Consider that avoid the use of organic solvent for sample treatment and analysis. Also require low energy instrumentation. But the idea is at the start of this trip, how render more sustainable this device, and start to use paper. And if at the start the idea is to use paper to deliver a more sustainable electrochemical device. In this roadmap, I demonstrate that paper is not only a sustainable substrate, but really can improve the electrochemical performances of the electrochemical device, and also can break down some limitation of a classical polyester-based device. So, which is the starting point? The starting point is the printed electrochemical sensor on polyester, which we print in our lab by screen printing technology. And we modify this sensor with nanomaterial like gold nanoparticles and carbon black, or also with the biocomponent like enzyme and embodied nucleic acid to deliver biosensor. I would like to show you that I select carbon black as a nanomaterial to modify the electrode, because now more than 10 years ago, I started to use this nanomaterial to improve the electrochemical performance of the electrode. And why I have selected this nanomaterial? Because it's characterized by low cost, €1 for 1 kilogram. In addition, it's very easy to produce a stable dispersion. It is very important when you think about mass production of the electrochemical sensor, because of course, screen printing technology deliver a mass-produced electrode, but it's important also that during the modification step, we have to follow the same approach. So drop casting is again a mass production approach for modification of electrode. And I'm happy to say that if I start to use carbon black more than 10 years ago, and I remember that the first article that I submitted was rejected because the review say me is a characterization of another nanomaterial. I'm happy to say that now, after my work, a lot of people use this nanomaterial to improve the electrochemical performance of, for example, printed electrochemical sensor. And and regarding the paper-based device, to be honest, there is two main articles that inspire me to start this roadmap. The first one is by Professor Whitesides from Harvard University, in which in 2010 highlight the importance of the use of paper-based analytical device as a diagnostic tool for developing world, for diagnostic in developing world. Consider that this device match the assured criteria established by World Health Organization, in which assured means affordable, sensitive, specific, user-friendly, rapid, robust, equipment-free, and delivered to those unit. And recently was updated with the reassured in order to have a real sample analysis, easy of sampling. Consider also the vision of telemedicine. And because you can see that this approach is colorimetric approach, and when we work, for example, with the complex matrix like capillary broad, it's not possible to have accuracy system using this type of matrix without sample treatment. So the first article that used this approach, but with electrochemical detection, was reported in an analytical chemistry journal by Professor Harry Group, in which they produced a three printed electrode on filter paper and modified with the Prussian blue as electrochemical mediator, and with the glucose oxidase to detect glucose, lactate oxidase to detect lactate, and uricase to detect uric acid. But of course, if we put a drop of water on filter paper, there is the diffusion of the solution tank, the capillarity-driven properties of the paper. So we need to create hydrophobic region that delimitate the hydrophilic one. In this case, they use a monomer, which is cross-linked under UV to produce a hydrophobic polymer, and after the excess of monomer was removed by organic solvent. But how to again reduce for example, use organic solvent also during the production, and how to render more sustainable this approach to create a microfluidic pattern. So our choice is was and also is the use of wax printing. So we use wax to create hydrophobic region, and thus to create microfluidics. In this case, easily, we design the pattern. So the green part is in the zone in which there is the wax. After, by wax printing machine, we print the microfluidic pattern, and after, by heating process, so means 1 minute in oven, there is the percolation of the wax in the paper network in order to have a 3D system. And after, we can print the electrode. So the first thing that I would like to demonstrate, if we can use office paper as support to print the electrochemical sensor. And my answer is yes, of course. And we demonstrate the possibility to use the classical office paper as support to print the electrode, but in 2 cases, both for sensor and both for biosensor. The first example that I would like to show you is detection of zinc ions in biological fluid, for example, in serum and sweat, by stripping analysis technique. In this case, instead of mercury, consider that mercury is to avoid for its toxicity, we select the bismuth film. And so we have the accumulation of zinc ion close to the electrode, forming an alloy with the bismuth, and after there is stripping analysis. In this case, we have the peak. And this is the calibration curve with detection limit equal to 25 nanogram per milliliter. And after, also we carried out the interference study and consider the working solution and consider the electrochemical parameter. We demonstrated that this sensor is able to detect zinc ions also in presence of iron, copper, magnesium, lead, and nickel. And also we demonstrate the accuracy of this device by recovery study using serum and sweat. And this is the article. In addition, in order to demonstrate the possibility to use this sustainable support also to develop a biosensor, I would like to show you an interesting example applied in defense field for detection of botulinum neurotoxin A and C. And another important thing of the paper, it's also the possibility to be incinerated after the measurement. This is, for example, it's very important in defense field because there is one pillar in this field related to decontamination. If I can burn the sensor, of course, I can reduce the cost of decontamination of the device. In this case, we study how the botulinum toxin work. And this toxin is able to cleavage a peptide, namely SNAP25. In this case, I reported the 3 cleavage sites of botulinum toxin C, A, and B. And we selected a sequence of this SNAP25 in order to have a synthetic peptide which constituted of 14 amino acids, in which in red highlight the cleavage site of botulinum toxin A, and in red and black the cleavage site of botulinum toxin C. So consider this, how is conceived this device. We immobilize this synthetic peptide labeled in this part with the methylene blue as redox probe, and this part with thiol group in order to harnessing the affinity of thiol with the gold nanoparticles. So we print the electrode on office paper. We modify the electrode, the working electrode surface with the gold nanoparticles, and after we mobilize this selected and functionalized peptide. If there is present botulinum toxin A on C, there is the cleavage of the sequence of peptide, and so we remove the electrochemical probe, methylene blue, to the electrode surface, and we have the decrease of the response. So this is the approach. And we demonstrated that the high sensitivity of this device for botulinum toxin A and C, this is the calibration curve, we are able to detect for both botulinum toxin 10 picomolar. And in addition, we demonstrated that it's possible to have the selectivity also when we tested, for example, botulinum toxin E, because no decrease of the peak. Why? Because, of course, this cleavage site is not present in the peptide that we synthesize. And the idea, and we're working on that with the Italian Ministry of Defense to create an array in order with a simple drop of solution, we are able to detect different botulinum toxin. So this is the published article, and this is the Italian patent. So after that, we demonstrate that it's possible to use office paper as sustainable substrate. After we move to step forward, which is we demonstrate that it's possible to use a filter paper not only as sustainable substrate, but we can harness the filter paper to load the reagents in order to deliver a reagent-free device. And this is the scheme. And in this case, of course, the solution flow through the paper network. So it's the system is very different than office paper, in which the solution remains as drop, like in polyester-based sensor. In this case, the first example that I would like to show you is for detection of phosphate. In this case, for detection of phosphate, the reference method, so usually in the lab for example, environmental monitoring, is based on the formation of the heptamolybdate complex with the phosphate, and after reduced with the ascorbic acid to form a blue compound, so colorimetric detection. In this case, our idea is to replace colorimetric detection with the electrochemical ones, removing the used ascorbic acid, which is a not stable reagent, so need to prepare every day. And so we need heptamolybdate acid, strong acid condition that we preloaded in paper. And this is our starting point. In this case, again, we use carbon black as nanomodify or working electrode surface. We demonstrated the utility of use of carbon black in our previous work using a polyester-based sensor. This is the response without the modification of carbon black, and so better resolution the peak, and the lower sensitivity from 2 to 20 in the case of electrode modified with the carbon black. And also we are able to work at lower applied potential, because using carbon black, it's possible to work in the first couple peak without falling problem. And we demonstrate this also in the case of flow analysis. And to be honest, the idea to use of filter paper to preload with the reagent start from this work, because in this work, the reaction was happened in the loop. So the reaction between the heptamolybdate and phosphate, and after this complex go to the electrochemical cell to make the measurement. So means that the loop contains the reagent to make the measurement. And the idea is to, instead of have the flow analysis in which there is the problem of the bubble, there is of course a lot of solution to manage. Of course, also the peristaltic pump to manage the fluid. The idea is to replace this big system with a little one, which is a paper-based strip. So in the paper, we preload the sulfuric acid and the heptamolybdate, and after we dissolve the reagents by adding only the sample. So few microliter, for example, of the river water is able to dissolve the reagents, to have all reagents in the paper-based network, and after we are able to make the measurement. In the first CQ voltammograms, we demonstrate that we needed of carbon black because the red dashed line is the response without carbon black in the ink, and the black line is the response with the carbon black, so improving the sensitivity. In addition, we need the acid condition. In fact, without the preloading of the sensor with the acid sulfuric acid, we have no response because the strong acid condition is a requirement to form an electrolytic complex. This is the calibration curve. And another important thing, because this is the first work in which we use filter paper, we demonstrated good repeatability and also the capability to detect phosphate in distilled water. Why it is important? Because demonstrate that by adding distilled water, these few microliter are enough to dissolve the reagent. So we have an exact pH to make the measurement, and also we obtain the good response also in the case of river water. In this case, we need to add only few microliter of river water without other reagents, without adjust the pH. This is very important because it's really a paper-based strip ready to use. We ask to hand the user only to add a few microliter of the river sample to make the measurement. Another example that I would like to show you is a recently article published within the European Project Alliance, in which we use again carbon black paper-based sensor for detection of essential oil. And in this case, again, we demonstrated by preloading, for example, the strip with acetate buffer, which is needed for the measurement. We are able to deliver reagent-free device. In addition, also in this case, we demonstrated the advantage to use a paper-based carbon black modified electrode, because, for example, in blue line is the response in the case of bar electrode, in green line is the response in the case of electrode modified with the carbon black, in the case of thymol, and the same behavior we obtained in the case of eugenol, carvalol, which are other essential oil. And I would like to show you also the possibility to use this approach in the biosensor field. In this case, I would like to demonstrate this for inhibited biosensor. This type of biosensor are characterized by the fact that the target analyte is not enzymatic substrate like in the case of glucose, but it also the target analyte is the inhibitors. So we need to make the measurement in absence of the inhibitor, means the response of the biosensor, and in presence of the inhibitor. And if we observe a decrease of the response, we means that it's present the inhibitor in the sample. This type of inhibitor, for example, this type of inhibited biosensor, for example, are used for detection organophosphorus and carbamic pesticide, which is inhibitor of cholinesterase enzyme. So our idea is to create a device ready to use without the addition of the reagents, but only distilled water, only the sample, for detection this type of the inhibitors. As said before, when we had the sample or distilled water, we have the dissolution of the reagents, because in this case we need to make the measurement in absence and presence of the inhibitor. We have to make two measurements. So how to manage this point? This is the strip that we conceived. So the device is constituted of two strips. The first one for detection of initial enzymatic activity. The second one is for the measurement of the residual enzymatic activity due to addition of the sample. And in this case, we need to add the enzymatic substrate. And in order to deliver reagent-free device, we preloaded the enzymatic substrate, in this case butyrylcholine, in the yellow strip, so in nitrocellulose paper. And the triangle blue is the enzyme. So we preloaded here the enzymatic substrate, and we preloaded here the enzymatic substrate. And for make this measurement, we add only distilled water to dissolve the reagent and make the measurement to measure the initial enzymatic activity. And for the testing the real sample, we add the real sample here in order to have the reaction between the enzyme and the inhibitor present in the sample. And when the solution becomes dry, after we add the distilled water to make the residual enzymatic activity. If you observe a degree of the response, means that there is the inhibitor within the sample. So this is exactly what's happened when we make the measurement. So add the distilled water in the strip preloaded with the enzymatic substrate. So enzymatic substrate flow through the electrochemical cell in which is entrapped the enzyme. So we have the enzymatic reaction, which is produced teicholine, which is detected at the electrode surface modified with Prussian blue and carbon black nanocomposite. When we have to detect the sample, we add the sample in the close to the electrochemical cell here. We have two reactions. In this case are irreversible inhibition. And after we measure the residual enzymatic activity again by adding distilled water in this strip. And we observe a decrease of the response, and the decrease of the response is proportional to amount of inhibitor present in the sample. In this case, we use Paroxon as model, obtaining a detection limit of 3 ppb and the linear range up to 25 ppb. So in this case, we also demonstrate the accuracy of the system using complex matrix like river water and wastewater, and we can see the particulate, but we didn't observe the interference because if we preloaded the sample in opposite site in which we print the electrode, we exploit the porosity of the paper to block the particulate, so we have not interference. So we use the porosity of the paper to treat the sample, to contain the reagents, and also for microfluidics. In this case, in lateral flow configuration. And so we demonstrate this. And which is the next step? It's to harness the foldability and cutability of the paper for multi-analysis by design an origami configuration. In this case, we start again from inhibit biosensor. So to detect with the one single device different classes of pesticide. So the first class is related to organophosphor insecticide by using butyrylcholinesterase as reported before. The phenoxy herbicide can be detected by using alkaline phosphatase, and triazine herbicide like atrazine can be detected by using tyrosinase as biocomponent. So how it's possible using origami configuration for detection of multiple classes of pesticide? This is the concept. So we have 3 strips in which in each strip is present 2 couple of pad, one containing the enzymatic substrate, the red pad, the green pad, and one containing the enzyme solution preloaded. So how in this case make the measurement? In this case, we move from lateral flow configuration with the vertical flow configuration thanks to the origami design. And this is mainly possible only using paper and mainly possible using the electrochemical detection. I would like to show you, for example, the concept in the case of atrazine. So for the first measurement, we fold the first couple pad close to electrode surface, add distilled water, this is the configuration, and we make the measurement. For the measurement of the sample, we cut this part add the sample in the enzyme pad in order to have the reaction between, again, enzyme and inhibitor present in the sample. And after we fold again on the same electrode this couple pad and add distilled water in order to detect the residual enzymatic activity. So we use the first strip for atrazine detection, for example, the second strip for 2,4-D, and the third strip for the paroxone, considered like a model for organophosphopesticide. This is the calibration curve for paroxone in Aniane River water. Is another river water close to Rome. Also in this case, we ask to end user only the addition of few microliter to the red pad of the second couple of the pad. And this is the calibration curve for 2,4-D, and this is calibration curve for atrazine. This is the published article. So we demonstrated that it's possible to design the sensor, the paper-based device in origami system in order to have the multiple analysis by using the vertical microfluidic. So in this case, we're moving from lateral fluidics to vertical ones. In addition, I would show like really interesting for me and unusual approach of the use of paper. So we use paper as a reactor. This article, this idea, moving again, belong from this article in which we use carbon black to synthesize different on carbon black, different dimension of Prussian blue nanoparticle by exploding the different defect and purity of the carbon black and to catalyze the synthesis of Prussian blue. The idea in this case is it's possible to use the impurity of the filter paper to again synthesize the nanomaterial inside the paper-based network, avoiding, for example, the use of reductor, which is necessary for the synthesis of gold nanoparticle. The answer is yes. And we demonstrate this in the case of copper detection is wet and serum by using gold nanoparticle decorated paper. Indeed, we can see that the paper in optimized condition of volume, also the concentration of the precursor, we can see the pink color due to the synthesized inside the paper network of gold nanoparticles. And this is very important, for example, in the case of using filtered paper and gold nanoparticle as the modification of filtered paper, because if you had the commercial gold nanoparticle, so the dispersion, we observe no peak. Why? Because there is the aggregation of the gold nanoparticle on the filtered paper. If we use a decorated paper, we observe the response. Again, we demonstrate that it's possible to deliver reagent-free device because in this case, we preloaded the ACL for the measurement of copper. This is the calibration curve. This is, of course, the response without the modification with the gold nanoparticles. You obtain a good recovery, and this article was published in Analytical Chemistry Journal. So another important demonstration that the really versatility and improving of this device, low cost and eco design device, is the possibility to merge the different future described until now to really develop lab-on-chip of paper. And in this case, I demonstrate this idea in the case of this origami device for precision medicine in Alzheimer's disease. Why this topic? Because some drugs using in Alzheimer's disease for Alzheimer's disease management is based of inhibition of acetylcholinesterase, which is the key enzyme for nervous transmission. And because acetylcholinesterase is present in the brain, but also we have butyrylcholinesterase in the blood, the idea is to evaluate the residual enzymatic activity of butyrylcholinesterase in the blood, because of course each patient has different capability of this enzyme to be inhibited by the drugs. The reason for that, the response depending patients by patients. So the idea is of precision medicine. So in this case, this paper strip work like a glucose strip. So we need to measurement our target analyte in capillary blood. If in the case of glucose strip is glucose, so easier. In our case is the enzyme. So we have to measure the residual enzymatic activity. In this case, the enzyme is the target analyte. So we preloaded the pad with the enzymatic substrate. And because, of course, we work with the whole capillary blood, we add additional layer of vivid plasma separation membrane, which is able to treat the capillary blood for capillary blood to serum. So by adding a few microliter of capillary blood, we pass in vertical flow by in serum, the serum that pass the first layer of the membrane contain the enzyme, which react with enzymatic substrate preloaded in layer 2, and after we carried out the measurement. So this is the calibration curve in the case of physostigmine taken as model, and using rivastigmine and dorimpidzil, which is a real drugs. This work was carried out in collaboration by Tor Vergata Hospital. And in addition, very good results were obtained when we compare the degree of the inhibition with the butyrylcholinesterase and acetylcholinesterase. Demonstrate that our idea is good, that there is a correlation between butyrylcholinesterase in the blood and acetylcholinesterase in the brain. We also demonstrate the capability to use this device both in venous blood that in capillary blood, and this is the device. So we use in this case the design strip combined with the Sensit, which is a potential miniaturized smartphone-assisted potentiostat, commercially available by Pansense Instrument. And so we are able to really deliver a lab chip on paper, because it is able to treat the sample, to contain the reagent, to make the measurement, also in complex matrix like capillary blood. So after that, so we demonstrate that it's possible to use the device to improve the electrochemical performances, but the question is, it's possible to break down some limitation of classical polyester-based sensor? Again, my answer is yes. And we demonstrate this in two cases. The first case for aerosol sample detection, so the target analyte in aerosol sample, and for the target analyte in solid sample. In the first case, this is the starting point. So this is my old work when I was a PhD student, in which you have to deliver a combined biosensor for nerve agent detection. And in this case, we have polyester-based sensor. So for detection of target analyte and aerosol phase, we have to sample in the air, put there in the system in which was preloaded the solution. So the idea is it's possible to reduce all this system, harnessing the properties of the paper. My answer is yes, because we use the porosity of the paper and the humidity like the activator of the system. How? We demonstrate this in the case of another chemical refrigerant, which is the mustard agents, because this mustard agents is able to inhibit choline oxidase enzyme. So this is the system, again in origami system. The idea it was to, in origami device, we preloaded close to electrochemical cell the enzyme, and another pad the choline oxidase. So we preloaded, we wait that become dry and die, and after put each other. So we put this strip in this bottle, in which we generate the mustard agent gas, and the humidity of this aerosol it's enough to weight the pad and dissolve the reagents and make the measurement. So we demonstrate this. Of course, this measurement with the real mustard agent was carried out not in my lab, but in Bundeswehr Institute of Pharmacology and Toxicology in Munich, we are able to really detect low concentration mustard agents in order to deliver in a paper street an alarm in the case of this type of chemical warfare agents. This they published the article, and we demonstrate also the possibility to detect the target light for precision agriculture. The idea is to put some paper-based flour on the soil in order to evaluate when there is a misuse of pesticide, because there is a large amount of pesticide, there is the deposition of the pesticide on the soil, and so the percolation and the pollutant of the aquifer, so drinking water. And again, the idea is to work with this pad like in origami configuration to detect different pesticides. In this case, we test also glyphosate. This is the article. And I would like to highlight that in 2021, one of the top emerging technologies was the breath sensor diagnosis disease. And my article regarding mustard agents and the article of Kandinser was published in the same year, and also can demonstrate that it's possible to use paper-based device, in this case for hydrogen peroxide detection in breath. So again, demonstrate that it's possible to use really a easy strip for detection target and light in aerosol sample without any additional sampling system, because the porosity paper work as sampling. And we demonstrate this again also for detection, for example, of SARS-CoV-2 in breath, starting from this work. This is the first article published at the world level during the pandemic event in 2020, was submitted, accepted, and in January 21 published. By the idea is to have the device to detect, to customize the device to detect the SARS-CoV-2 not in saliva but in breath, so delivering a smart mask. So in this case, we design this pad able to sampling the SARS-CoV-2 in the breath, and after to make the measurement. So this paper-based device is able to collect the exhaled breath sample and to act at the site for incubation within the sample and magnetic immunosystem. And this is, for example, the response for no positive patients, and this is for positive patients, so negative. So we select this like threshold, and by in this case we put the holder here, and we are able to observe the positive patients. We put the holder here again. We put in this position again, we observe the positive patients, and also by mixing all the three system, again we are able to evaluate the positive patients. I would like to see that this system is very sensitive, because positive patients in this case has 31 as a cycle 31 as a result from real-time PCR. So usually from lateral flow, classical one, colorimetric, the threshold is also 20. So we are competitive with the laboratory setup method about the sensitivity. This is the published article, also the cover in a chest sensor published the last year. And after demonstrate that it's possible to use paper to detect the target and light in aerosol fail without any additional sample system, we demonstrate this also for solid sample. And some example, for example, is for concrete molding, so a little bit different. In this case, this is again the starting point. So we demonstrate that it's possible to evaluate the corrosion of the concrete structure by measuring the potential between the bar and the reference electrode. In the classical method, so the method used now, they use a wet sponge and they use the bulk copper sulfate electrode as a reference electrode. In this work, we demonstrate that it's possible to miniaturize the system because we use, of course, the bar, and we use the printed electrode, in this case on polyester, and to close the electrochemical cell, we use hydrogel loaded with the KCl. And we demonstrate that it's possible with a really cost-effective system, evaluate the corrosion level of the concrete structure because change the potential. For example, increasing the chloride content in the concrete, the presence of chloride accelerates the corrosion. We observed a different potential, like in the case of carbonate. So, again, how it's possible to again render this system more sustainable using paper? My answer is yes, because we replace the electrolyte gel with the polyester-based cells with the paper. See, easily, we print only the reference electrode on the paper, and we replace, instead of the gel, the few microliter of KCl in the filter paper. We, for example, apply this for evaluate the corrosion also in concrete structure, in this case in artwork present in Milan, in which there is the artwork is present the chair, the iron chair in the concrete, and we are able again to evaluate the corrosion level of this chair, demonstrating the accuracy of the system. And after, we also demonstrate if in the previous case we replace the classical system with a miniaturized one. In the case of chloride content, actually the only system is invasive because they need to take some sample concrete to go in the lab, treat the sample, and use the laboratory instrument setup method. In this case, we easily again use paper to solve this issue, to measure the chloride on the surface of the concrete structure by using a potentiometric device in which we preloaded a non-solution or KCl in the first layer, working a reference. We add a junction pad and we add or distilled water to dissolve the chloride on the concrete, or KCl in the case of calibration curve. So in this case, by adding only 1 drop of KCl, 1 molar in the first reference pad, and distilled water with the pad in contact with the chloride, with the concrete, we are able to evaluate the corrosion of the structure. Again, we demonstrate this and published in Analytical Chemistry journal. So, after that, we demonstrate that it's possible to use this paper device also to overcome the limitation to detect the target analyte, an aerosol sample, and solid sample, but the versatility of the paper is able to solve some additional issue in the case of the other device. Again, my answer is yes. For example, we use paper to render this device, which is a plastic device, in which is present gold working electrode like bar, copper bar like a counter electrode, and a silver bar like a reference electrode. Because it's not easy to modify the electrode because it's embedded in polyester-based system. In this case, we use the paper strip to preload the reagents. Means, for example, to detect glucose in tears, we preloaded the Prussian blue, carbon black nanocomposite, and glucose oxidase. And we demonstrate that changing the strip, it's possible also to detect different target analyte. Indeed, by, for example, adding a strip preloaded with uric acid, you detect uric acid. If you preload this strip with lactate oxidases, we are able to detect lactate. This is published on Chemical Communication. And in addition, another question is, starting again with this system that we developed for SARS-CoV-2 in saliva, when we talk with the company, they said us that it's very important to have not to waste a solution, because it's difficult to manage, especially because we don't know at the start if we have positive or negative patients. So again, we use paper to solve this issue. In this case, we use this absorbent pad in this system in order to really have easy to use device, also if a competitive immunoassay. In this case, this system work like by adding the sun drop of the sample. We wet that happen the solution, so there is the construction of the immunological chain. After we add 2 drop to remove the embodied reaction, to remove the reagents, but the reagents now is not needed to wash the solution, but the solution go through the paper-based device. So in this case, the paper strip work as passive pump, also as a waste reservoir. And after we add 2 drop of the enzymatic substrate in order to have the reaction. In this case, we preloaded also with a chloro compound that become light blue, indicates that everything works well. This is again the patent in collaboration with Italian Ministry of Defense, and this is the published article. Again, we obtain a very good sensitivity with able to detect also really a high CT number like this 35. And another recently our article is related to combine also paper-based device with the 3D print holder. In this case, we detect phosphate in soil, and we use the paper, the 3D printed, also to treat the sample, and by grinder the sample of soil, and we use a pad to contain reagent to make the measurement of phosphate in soil. So, for example, this is the response of phosphate in soil. And this is the calibration. This is the measurement using our system, and this is the results of our system. This by using the reference method. This is the recently published article on Talanta. And in addition, we have conceived this device also like a lab on skin. In the case of wearable sensor, we demonstrate that it's possible, for example, to detect cortisol in the sweat by a competitive system in which we preloaded labeled cortisol with the cholinesterase enzyme. And after, when we have the sweat on the skin, there is the wet of this part, there is the flowing, and we have the reaction close the lateral surface. We ask to end user only the close to this pad that contain the enzymatic substrate to make the measurement. And this is the response during the cycle activities, the published article. And recently we demonstrate that it's possible also to detect different target and light in continuous. In the case for pH measurement and sodium measurement is very important, for example, for the detection. And in this case, we have the sampling pad, and we have the pad that work like again reservoir and passing pump, and we demonstrate this that by measuring pH and sodium. And this is very important that we study the hysteresis, and we can see that starting from pH 7, moving to pH 4, and come back to pH 7, you obtain the same results without memory effect. Demonstrate that it's possible to detect in continuous without memory effect the pH, also sodium concentration. This is the continuous analysis, and we test the sample only at the end by reference method, obtaining the good agreement. So with the reference method, we detect the amount of sodium, for example, only at the end. In our system, we are able to detect in time because thanks to miniaturization, so need low volume and also microfluidics. So this is the article. So in this presentation, I demonstrate that it's possible to use paper not only as sustainable substrate, but also to deliver reagent-free device, multiple analysis, use paper as a reactor in order to synthesize inside the paper-based network the nanoparticles, lab on chip, and also to break down the limitation of polyester-based sensor, so detection by detecting the target light in a common sample like aerosol sample and solid sample without any additional sampling system. And this is some review published regarding this topic by my group, and which is the next step in which we are working, an organ chip of paper. And this is the European project, EC Pathfinder Horizon Europe, in which I'm the coordinator, in which the idea is to break down the organ chip field using paper. So another step forward, the demonstration of the versatility and utility of the paper in the device. And just a few words about my spin-off company, in which I'm CEO, in which we are working for development of point of care for diagnosis of cystic fibrosis. We started this activity before the COVID, and I'm happy to say that the last year, the European Commission highlighted that biosensor could be useful to treat the rare disease, and cystic fibrosis is the first one. So the last thing is to say that if I start from this work, which is a future, it was a future of analytical chemistry. Recently, I published a perspective, so like now the new future in analytical chemistry, which I report exactly the roadmap that I carried out in my group. This is the cover letter. I would like to cover page, sorry, and this is the funding. So thanks to the funding, thanks especially for all people that work with me, Vincenzo and Luca that work in wearable device, Laura Fabiani that work in SARS-CoV-2, Nargi that work, for example, phosphate detection in soil, and Ludovica also in 3D printing, and Georgia, Ariane, and Matteo from Med Company, and all of you for the kind attention.
Thank you, Fabiana.
Yeah.
Okay, thank you. You have a lot of questions. We have good news for you.
Thank you.
Okay.
Yeah, of course.
The first question is, I am taking here. The first question is about the origami sensor. What is the biggest challenge considering the electroanalytical performance of the origami sensor?
Yeah, in the origami is better the microfluidic in vertical flow respect the lateral flow, because in lateral flow usually we can lose some reagent during the flow. In the case of vertical microfluidics, we pass in different layers, so means that there is less contact between the paper and the reagents. So we didn't lose the reagents absorbed or trapped in the paper. And it's possible only with the electrochemical detection, because in the optical one, it's difficult to work in origami, because if our sensor is at the end, we are not able to see. So the real challenge is to exactly conceive the device in order to have each layer for each needed step for the measurement. For example, if I need to treat the sample, I can use the first layer. And using the paper, usually the paper should be selected, consider the type of the treatment that you need. For example, if you need only to remove the particulate, we use a porous paper with the porous that block the particulate. If you need to treat capillary blood, of course, more difficult, in this case, we select another type of like paper. And the other layer could be the reagent to add. For example, it's possible also to move the different pad to customize the detection. So I think that really origami is a useful thing to harnessing the versatility of the paper in order to treat, to control the reagent, to make the measurement.
Okay, thank you. We have another one about the origami as well. This origami approach can be used on large scale or just for the small volumes.
Yeah. So sorry, can you repeat the question?
Yes, of course. The origami approach can be used on the large scale or just for the small volume.
Yeah, depending. So of
Mhm.
course, the advantages of the origami is work with low volume. Another things that I forgot to say, it's when you work with high volume, you can exploit the porosity of the paper also for the preconcentration. Because for the paper, when you work with the filter paper, we can also have the preconcentration on the sample in two ways. Or you, for example, put 5 microliter wet that become dry, 5 microliter that become dry, and step by step, and after you can dissolve the target light with 5 microliter, so there is preconcentration depending the step. Also, there is a interesting work by Professor Harry Group, in which, for example, use a paper layer, so like origami, pass through, for example, a large volume of the sample. There is the preconcentration after you take the paper-based pad and make the measurement. So if you need high volume, it can be better because you pass through. So we have preconcentration and we make the measurement.
We have one big question. I try to make an abstract for you.
Yeah.
Uh, do paper sensors using signal inhibition show different stability compared to traditional system? I think the question is to compare the traditional system to the sensors, like the
Yeah.
scripted sensors.
Yeah. Regarding the stability, usually the main challenge in biosensor is the storage stability, because usually I say that is that valley from bench to the market. Because if you produce a biosensor which is stable in the fridge for one day, it's impossible to reach the market. The advantages of the paper that usually the bio component is entrapped, and the paper is like a biocompatible material. So sometimes it's very comfortable for the enzyme to be entrapped also in dry condition in the paper. So the storage stability of the biosensor for enzyme especially is usually improved using the paper instead of the classical polyester.
We have another one. The big one. Do peptide modified biosensors require special storage condition or is conventional storage is sufficient?
Now, in this case, for this peptide, we need to be in the fridge, not like enzyme at room temperature. So this is the limitation of this sensor. But it's very important to consider that actually the botulinum toxin test, so means that if we have the sample, you have to test the botulinum toxin, the reference method is the use of the mouse. So you put the sample in it or drink by the mouse, and we wait 5 days. So absolutely no sustainable, because of course you use animals and for the time. So for the 5 days, especially we have not a good period, especially for the management of terrorist attack and so on. 4 days is too much. So it's very important to have a smart device for chemical and biological warfare agents.
Okay, we have the last one. Regarding the construction of electrochemical sensor, is it necessary to retract the paper used as on substrate?
Yeah, in our case, my concept is always reduce the cost, because we are in Italy, we are not so big fund, so it's very important to reduce the cost. The reason for that, instead of the classical Wattman, we use classical filter paper, because it is really a lot more cheaper than Wattman paper, and we use this paper like we received. The only treatment that we made is when we had works for microfluidics, but at this time we have not necessary to treat. Also, for usually you can treat the paper to immobilize covalently the enzyme. In our case, we prefer entrapped enzyme in the paper network, or also, for example, use magnetic beads close to the paper to immobilize the immunological chain in order not to treat the sample and easy to use.
Okay, Fabiana, I have, I think, no, I think it's finished for the questions. So, on behalf of the SBE, we thank you again for participation in our second webinar. Thanks so much. I think the audience liked so much because we have a lot of questions for you. Thank you so much, Fabiana.
You're welcome. You're welcome. Okay, thank you. It was
Okay.
it was my
Thank
pleasure.
you. Bye-bye.
Bye.
Okay, bye-bye.